Mechanics. Lecture 1. Motion in centrally symmetric field. Part 1. Features of movement in the centrally symmetric field. Centrally symmetric, or central, field is a field whose source is point-like and located at the center. If a particle is in such a field, then its potential energy and the force acting on it depend on only the distance between the particle and the source of the field. Direction of the force acting on the particle always coincides with the direction between the particle and the source of the field. When moving in the central field, the angular momentum of the particle relative to the center of the field is conserved. Moreover, the conserved angular momentum and the radius vector of the particle are always perpendicular to each other. Therefore, when a particle moves, its radius vector always remains in a plane perpendicular to the direction of the angular momentum. Therefore, the radius vector always remains in one plane, so the trajectory of a particle moving in a central field lies entirely in one plane. Therefore, the motion of a particle is two-dimensional, and accordingly, will be described by two coordinates. When describing motion in a central field, it is convenient to use a polar coordinate system. In polar coordinates, the field depends only on one radial coordinate, and the problem of solving the equations of motion is simplified. One of the features of the solution of the equations of motion in the central field is that the angular coordinate always changes monotonically. So the derivative of the angular coordinate with respect to time, that is, the angular velocity, never changes sign. Thus, the angular velocity of the particle is always directed in the same direction. Part 2. Reduction of the two-body problem to the problem of motion in a central field. Two-body problem is the problem of the motion of a system consisting of only two interacting particles. Like in the problem of motion in a central field, in the two-body problem the force and potential energy of particles depend only on one parameter, the distance between the particles. So two-body problem is reduced to the problem of motion in central field. The two-body problem turns out to be mathematically equivalent to the problem of central field if we use a coordinate system centered on one of the particles. Then the potential energy will depend only on the radius vector of the second particle. Note that the coordinate system centered on one of the particles is not inertial, since it will move along with the motion of this particle. In addition, the mass of the second particle must be set equal to the so-called reduced mass. Reduced mass is equal to the ratio of the product of the masses of the first and second particles to the sum of the masses of these two particles. Having found the trajectory of the second particle in such coordinate system, by inverse transformations we can find the trajectories of both particles in inertial coordinate system.